After covering the inversion rule, that's section 5.9 in your lecture notes, we're almost finishing this big chunk of content, which is section 5, that provides you a lot of the basics of how to differentiate with a lot of different rules. The final topic of section 5 is parametric differentiation. Parametric differentiation can be really useful in physics because many times we have functions defined in terms of a parameter. A practical example could be looking at positions x and y as a function of time, which in a parametric function would be written like x equals some function of time and y some other function of time. Or you can also write that in this case x would be a function of time and y also a function of time. Functions like this could be telling you, for example, how a given particle is moving in x and y positions. If these functions involve sine and cos, maybe you could be looking at how the position is changing as a particle goes in a circular orbit. But it doesn't really matter what it is describing. Parametric differentiation allows you to differentiate functions that are defined in terms of a specific parameter. A really great thing about parametric differentiation is also how intuitive it is if we use Leibniz notation. Let's say that we want to calculate dy dx, but we don't really know how y and x are related unless we look at how they are each related to another parameter, in this case time. And your best hopes really are true. And again, we can think of these infinitesimals as behaving. In this case, the properties are similar to being a real quotient, even though it is not. And it means that to calculate dy dx, you can actually calculate dy dt and then divide it by dx dt. You can think that you're kind of cancelling the dt's and then ending up with dy dx. The other way of writing this is with fractions. Dividing by something also means multiplying by 1 over that. So we can also see that this is equal to dy dt dx. And again, you can see that this makes sense and it's very intuitive with Leibniz notation, because you would be able to cut the dt's and you end up back with dy and dx. To make sure that you understand, let's think of a practical example, a very simple one. Let's say that we're looking at this function and that this is cos of t, and for y we have sine of t. If we want to use parametric differentiation, and our goal will be to calculate dy dx, we can't really do it because y is not a function of x is not a function of y. They're defined in terms of the parameter t, but we can use parametric differentiation to do that. And the two key ingredients are dy dt and dx dt, and then we just need to divide. It's relatively straightforward. So step number 1, we calculate dy dt, the derivative of sine t in respect to t is cos t. And step number 2, dx dt, the derivative of cos t in relation to t is minus sine t. And by using parametric differentiation, then dy dx is just given by the ratio of dy dt, that's cos of t, over minus sine of t, which also means that you can write this as minus cotangent of t, being your final answer. In this case, with these simple functions, dy dx is minus cotangent of t. So congratulations for making it to the end of section 5, at least the video playlist. I hope that you've learned a lot and that you've been able to revise or recap a lot of the differentiation rules, and that you've started doing a lot of problems and practicing a lot, because as previously with limits and differentiation from first principles, the trick, the ultimate tip, is to practice. And therefore, I would recommend that you have a careful look into the lecture notes. After section 5.10 comes section 5.11, where you have a range of solved examples, also based on supplementary questions and also on things that come up in the exams, also showing you the level of detail and explanation that is expected from you. And if you have any specific question, make sure that you tell me via Teams and email, and in the discussion sessions we'll be able to cover them. And if we don't, again, make sure you get in touch so that you understand all the details and you really nail Physics 101 and therefore your degree. So this means it is the end of section 5, and provided that you do a lot of the examples on the lecture notes and that you bring up any questions that you may have during the discussion sessions and during the week that we're covering section 5, you will be ready to move to section 6, where we go to a higher level, literally, higher order derivatives, what they can be used for, their physical interpretation, and also as we prepare to start talking and discussing about functions of more than one variable. So it's going to be spectacular.